Today we're going to be talking about a nice paper by Aaron Neighbor and Daniela Valtorta titled Volume Estimates on the Critical Sets of Solutions to Elliptic PDEs. This paper has a nice mixture of PDEs and some ideas from harmonic analysis that allows us to prove some novel results in a low regularity setting. So first, a motivating question. Suppose we're looking at a second order elliptic PDE, which is homogeneous and has Lipschitz coefficients. And let's say we have a solution U, which is defined on the unit ball. We can look at the singular set or the critical set of U, both of which tell us where the gradient of U vanishes. The main difference being that for the singular set, we also look at a level set of U. With the relevant set of interest depending on whether this coefficient C of x is identically 0 or not. But for either one of these sets, depending on the setting we're in, we can ask how big can these sets be? First, in terms of Hausdorff dimension, which is known to be n-2 for non-constant solutions, or we can ask the Hausdorff measure, we can ask for bounds on that. And we can also ask how wild can these sets be? For instance, could they be dense in the ball of radius 1/2? Are they rectifiable, which is a regularity property? And so on and so forth. So in the paper, there are effective versions of these sets, which are slightly larger sets based on quantitative positions, which also take in a scale parameter, r. And from here forth, we'll only be worrying about the critical case, where that constant C is identically 0 for simplicity, but many of the techniques will work in general as well. So we have a definition for the effective version of the critical set, which is given by this slightly intimidating looking condition. It can be thought of informally as the points in the complement are the points where the size of the gradient is comparable to the size of the function up to a suitable scaling. And in particular, this contains the classical critical set, since if the gradient vanishes at a point, then for every r greater than 0, the left-hand side here is going to vanish and the inequality holds trivially. So the main result of the paper, theorem 1.1, says that if we have a bound on this quantity called the frequency of U, which we'll define in a minute, then we can find a constant depending on the dimension and the Lipschitz constant, such that we can control the volume of a tubular neighborhood of this effective critical set with a bound of the form c to the lambda squared times r squared. And in particular, since we have r squared here, this is going to imply bounds on the n-2 dimensional Hausdorff measure of the critical set and this effective critical set, which is slightly larger. So the frequency function is going to be a very important object of study in this paper. We'll focus only on the harmonic case from here forward. This harmonic case is actually quite representative of the general elliptic case, since we aren't going to exploit anything specific to harmonic functions too much. We won't make use of analyticity or the mean value property, for instance. So for a fixed solution U, its frequency function is given by this L2 quantity. We take in both a point and a parameter r that we'll call the scale frequently. And oftentimes this parameter x is suppressed because we just imagine working at a fixed point x and asking how the function changes as we vary the scale parameter. And this has some nice invariance properties, so it's unchanged if you add a constant to u or if you multiply u by a constant. If you dilate u, then you also have an invariance property. We also have the very useful fact, which is that this is monotone increasing in R for a fixed point x. Moreover, if the frequency is equal at two different scales, R1 and R2 for a given point x, then that tells us that the frequency is actually constant for all values of R. And in that case, u is a harmonic polynomial, which is homogeneous about the point x, which we'll talk about a little more in a second and denote by HHPs. Moreover, this frequency function is an extension of the vanishing order, in the sense that as we send R to 0, the limit will always exist by monotonicity. Then this frequency function converges to the vanishing order of if we subtract off the value of u at the point x, and then look at the vanishing order as that function goes to x. So we think of the vanishing order as kind of at scale 0 what this frequency function is telling us. But we also can make sense of this vanishing order through this frequency function at larger scales. So a quick digression to homogeneous harmonic polynomials. These will also be a useful tool. And as the name suggests, these are harmonic polynomials which are homogeneous about some point x. In particular, since they're polynomials, this implies that it can be written as a sum of monomials of all the same degree if you translate suitably. So for instance, we have these two homogeneous harmonic polynomials of degree 3 and 2, both homogeneous about the origin, which will be the main case we'll be thinking about for simplicity. And lots of these exist. In fact, any harmonic function on the unit ball can be written as a sum of a bunch of homogeneous harmonic polynomials, where the AJs here are coefficients, and these PJs are HHPs homogeneous about the origin of degree j each. There are also variants of this that we can do if our function is defined on a larger domain, for instance, where instead of doing HHPs that are homogeneous about 0, we can do HHPs that are homogeneous about other points x, and we get different coefficients in that case. So technically, these AJs and PJs have a dependence on the point x that we're choosing to expand about, but we suppress this and just remember that the expansion's about x whenever these show up in relevant contexts. And as mentioned before, for HHPs, the frequency is equal to the degree for all values of R, and also for R equal to 0, since that's defined by taking a limit. Moreover, we can expand our frequency function in terms of these coefficients of HHPs given by this quotient here. And here the formula is written to be about the origin, but again, if we take expansions here about points other than the origin, then we also have the analogous formula here. Okay, so a useful property before was that if the frequency agrees at two different scales and a given point x, then we're actually an HHP, the solution u is an HHP homogeneous about x. And now we have a nice extension of that result, which is that if our function, our solution u, is delta pinched between scales R2 and R1, meaning that the frequency changes by less than delta when plugging in those two different scale values at x, then we are going to be well approximated by HHPs in a number of ways. So there's a string of results proved that are all useful for understanding this pinching phenomenon. It's shown, for instance, that the only time pinching can happen when delta is small enough in a suitably universal sense is when the frequency is close to an integer. Here R is anything in this range, possibly with some multiplicative constants that I suppressed. There's this nice result that in the denominator of this expansion, which is sometimes called little h of r, which is useful for various reasons that we won't get into, then being pinched tells us that one particular term dominates that sum at scale r. Also, at this scale, u can be well approximated by a homogeneous harmonic polynomial, which, to be precise, it's really we're applying a sort of tangent map to u, which is defined more carefully in the paper. And also, if u is pinched at multiple different scales or scale pairs, then the approximating homogeneous harmonic polynomial is going to be the same at each of those scales. And moreover, we can say which HHP it is. It's going to be the lowest non-zero term in the HHP expansion is going to be what approximates it well. So these results are going to lead to this key dichotomy, which is that when we change scales, when we vary this r parameter and make it smaller, then either the frequency is going to drop by a fixed amount, i.e. it's going to drop by at least this delta once delta is chosen in a universal way, or we have the pinching phenomenon, in which case we know the frequency has already almost dropped to the vanishing order at x. That is the limit as we send the scale parameter to 0 already. Some other useful facts, taking advantage of the fact that we're approximating by these HHPs. First, it's not too hard to see that if you have an HHP that's homogeneous with respect to two different points, then it's actually going to be invariant with respect to the line between them, i.e. that directional derivative is going to vanish. And after after changing variables or applying a rotation if you prefer, it can be viewed as a function of only n-1 variables rather than n. And we can do even better than that in some cases. It turns out that if we have n-1 sufficiently small different directional derivatives of our polynomial, then we're actually in the case where p, the polynomial, must be degree 1. That is, we get that it's a linear function, and if we apply a suitable change of variables, then p can be viewed as a function of just one variable even. Moreover, there's a nice contrapositive to this, which is that if we have a higher degree HHP, that is degree at least 2, then it can only have small derivatives in some suitable sense in at most n-2 directions. And moreover, in this extreme case where we have n-2 almost invariant directions with small directional derivatives, then our polynomial can be approximated well by an HHP which actually has n-2 invariant directions. And this is useful since it can be viewed as an HHP on the plane or an HHP of two variables. And these are easier to understand than in higher dimensions. And finally, in certain suitable senses, the delta pinched points, where we know we have good approximation by HHPs from the results discussed over here, the delta pinched points are going to cluster around planes of codimension at least 2 in some senses. So with this machinery established, we can now prepare for the inductive argument that will lead to the volume estimate. So we have this concept of a good scale ball for a solution relative to a given degree d, which just means that the frequency for every point in the ball at that scale isn't going to be much bigger than d. And d is an integer here, the only values that we can be pinched near. Also, if we fix a radius r greater than 0, which we're going to think of as we're going to think of that as like the R in Hausdorff measure, the bound that we have for the radius, the upper bound. So we're going to think of this as something small that eventually we're going to send to 0. But anyway, for fixed R greater than 0, if we have a good ball relative to D, then we can define this quantity Rx prime, which is going to tell us when the frequency drops below D. In particular, we know, since the limit has to be an integer, that if it drops below D, then it has to eventually get to D minus 1 or possibly some smaller integer. And we also give ourselves even epsilon of room here. And Rx, which we can take to be the maximum of this parameter Rx prime, and our fixed R that's eventually we're going to want all our radii to be less than R. So our hope is that the balls that we use will end up having the maximum here be R, so our radius will be small enough to get the Hausdorff estimates. So now, instead of looking at the effective critical set as defined before, it turns out that instead it suffices to estimate the region of points, or the set of points where the frequency is at least 3/2 at scale R, and this will contain our effective critical set at scale R. So we split this into a good part where all these Rx values are comparable to each other in a small ball, and a bad part consisting of the rest of the points. And by looking at each of these parts separately and using the tools developed in the previous parts, then we get this useful proposition 3.36, which tells us that we can cover both the good and the bad part by a bunch of balls. We have good volume control properties on the balls for the n-2 dimensional estimates that we want. And at least one of the following two property holds for each ball. The radius is at most R, or failing that, the frequency will drop down to at most D minus 1 plus epsilon. So essentially we'll drop to the next lowest integer. And this is going to be key in our inductive argument. So I won't go through this in detail. Instead, I'll do some pictures, and the details are in section 3 with a nice overview in section 2 of the paper. So the idea is, if R is the effective critical set here, where this picture is a little bit misleading because it should really be something codimension 2, but it's easier to draw this way. So if R denotes the effective critical set, then we're going to cover it with a bunch of balls, and we can get the first volume estimate with a constant that looks like constant to the lambda, based on how we choose our parameter epsilon here, which is in a slightly complicated way. But anyway, this is our base case. We get a bound that looks like constant to the lambda, where lambda is our bound on the frequency, that is n at the origin, scale 1 is controlled by lambda. And for simplicity, I'll just assume lambda is an integer d here. So now, on any ball which has radius bigger than r, we're going to zoom in on it and apply this proposition again with some balls. And maybe some of the balls are good and actually have radius less than r. So I'll make that these black balls. Whereas the purple ones are still too big. So then on the purple balls, we repeat the process. We zoom in again. And again, maybe some parts are good and other parts not so good. So here the orange is too big, but the black parts are still radius less than or equal to r. And in each of these steps, we would get another factor of c to the lambda added, or multiplied on, excuse me. And we need to ask, do we have control over how quickly this terminates? But that's, the good news is this is taken care of by this proposition. since whenever in our cover we get a ball that doesn't have radius at most r, whose radius is too big, we know the frequency has dropped by 1. So if the frequency is lambda on this ball, then on this bad ball we know the frequency is at most lambda minus 1. And then when we zoom in on that and cover it, we know on these bad balls it's at most lambda minus 2. So while we do get this product of c to the lambdas, we know it's at most a lambda-fold product, which leads to the bound that looks like c to the lambda squared, which was exactly what appeared in the theorem. Okay, I want to just briefly summarize some of the changes that happen in the general elliptic case, but again, the harmonic case is pretty representative, modulo some technical details. One complication is that since we don't have constant coefficients, we're going to view the Aij coefficients in the PDE as being like a Riemannian metric, essentially. And several times we'll do things in quantities where we'll freeze this coefficient at a point and then look at the unit sphere with respect to that metric around the point that we froze it at. And this is also going to add an extra complication with some geometry, since that unit sphere is now actually going to really be an ellipsoid in Euclidean space. There's also a more involved definition of the frequency function, and monotonicity fails, but we do have an almost monotonicity, which tells us that if we multiply by a suitable exponential function, then that product of the frequency function times that exponential is going to be monotonically increasing. And since we don't have harmonic functions anymore, we have to do an extra step of approximation in that our solution to an elliptic PDE, we approximate that by a harmonic function, and then for the harmonic functions, we appeal to the harmonic case where we approximate by HHPs in, say, the setting of pinching. Finally, I want to just give a very rapid recap of the flow of ideas in this paper. The goal was to get Minkowski or volume estimates on the effective critical set of solutions to elliptic equations with only Lipschitz coefficients. One of the main tools we used was understanding this frequency function, which gives us a generalization of the vanishing order at a point that we can also make sense of at larger scales. And if this frequency is changing too slowly between two different scales, then our solution U is close to a homogeneous harmonic polynomial in several senses. Moreover, on the critical set, where the vanishing order is at least 2, then we know these approximating HHPs can only be almost invariant in at most n-2 directions. So their directional derivatives in at least 2 directions have to be large. And moreover, points in our effective critical set are going to cluster near a number of planes of dimension at most n-2. And finally, the inductive argument we just saw, which said that if lambda is an upper bound for our frequency, we can cover our critical set with a bunch of balls, get a bound that looks like c to the lambda, and then cover these by smaller balls by breaking it up and continue getting more bounds of c to the lambda multiplied on, but we only have to do this at most lambda times until all the balls have radius at most r, because when the radius doesn't drop below r, we know that the frequency drops by 1, basically. So some useful references if you want to learn more. Of course, everything here was taken by the paper of Neighbor and Valtorta. For some information on the frequency function, there are some nice notes here that can be consulted. And this text develops some of the theory of HHPs. Finally, there was a paper written before this by Cheeger, Neighbor, and Valtorta, which, although it uses different notation for some of the concepts, has a number of similar ideas and provides more details in certain results that are also used in this paper, which you can take a look at. I hope you found this talk useful, and if you have any questions, feel free to send me an email here.